and thank you for giving me an opportunity to talk here. Today I'm going to talk about some application of interlacing families. So the title of the talk is this one. It may take probably longer than 50 minutes, so sorry about that beforehand. I cannot say this result is amazingly good. Actually, this is a simple application of interlacing families. So the goal of this talk is to let you know the concept of interlacing families and how to apply them to a problem. Okay. Probably there are several things that you don't know and hear. So let's start with the interlacing families. The last year, the one spectral graph that has been published in Annals of Mathematics, and they proved. So this is Marcus Spielmann and Srivastava. So they proved the existence of an infinite family of bipartite Ramanujan groups. Of all degree, at least 3.
What do you mean by all degree? Minimum degree or?
No, all degree. So let me give you a definition about Ramanujan graph first. So Ramanujan, a irregular graph see, this is the Ramanujan means that the spectrum means the set of all eigenvalues. So the set of all eigenvalues is included in. So this spectrum means that the adjacency matrix. Okay, so the eigenvalue of this matrix of G is included in plus minus D because the largest eigenvalue of the irregular graph is D, and if a graph is symmetry, if a graph is bipartite, then the eigenvalues of a graph is a symmetry about 0. So it is also possible to have a minus D. Okay, so these are called just the trivial eigenvalues, and this number. Well, you may be wondering, where this number come from, right? This number comes from actually Allen-Bopan's theorem. So roughly speaking, Allen-Bopan theorem says, so given positive epsilon in here, so if G is a irregular graph with a sufficiently large order, then the second largest eigenvalue Okay, so adjacency matrix. Okay, so second largest eigenvalue of graph G is greater than equal to 2 times the square root to d minus 1 minus an epsilon. So this number is the minimum possible second smallest Laplacian eigenvalue if a graph is very large. Okay. So what? What we care about that? I mean, the second smallest, second largest eigenvalue. So here is a Chigg inequality. For the regular graph, say. So H sub c, this is called the Chigg constant. This is defined the minimum of all vertex subset that's I greater than equal to n over 2. So this is the set of edges between S and the complement of S, and this is the size of the set, and divide by S in here. So roughly speaking, this is kind of edge connectivity of a graph. Okay, so this inequality says we do not care about this one that much, but anyway, so this is this one, but we don't care about this one, so we only care about here. What does this mean? So this means that the difference between the largest eigenvalue and the second smallest eigenvalue, if the gap is higher, then roughly speaking, the edge connectivity is also large. Okay, so this means that if this is high, then we have a good expander in here.
And the sufficiently large order means is it depend on epsilon, right?
Yes, depend on epsilon. Well, actually, we can express this as a limit suit. Limit inf, actually. Yeah. So that's why people are interested in Ramanujan graphs. Okay, and then so the maximum possible gap between those two is actually d minus and just this one. Okay. So they show the existence of infinite family of bipartite Ramanujan graphs. But how about the non-bipartite case? We still don't know. Actually, someone proved actually the existence of Ramanujan graphs when degree is equal to the prime number plus 1. So this is actually related to Kelly graph. Well, they just show the existence of infinite family of this one. We still do not know explicit construction of this one. So, okay, so that is still open actually. As far as I know, the smallest degree that we do not know of a construction is probably 7.
So what is the degree here?
So the degree of the Raman, yeah, this one, yeah. So d is equal to 7. We don't know how to construct the infinite family. Explicit construction. We don't know the explicit construction of a 7D regular graph.
What do you mean by all degrees and this? Do you mean that for each degree?
Yeah, for each degree, yes.
Yeah.
Okay. If you
And how about when d is equal to 2?
No, d is equal to 2 is just a cycle. There's nothing to do here. Okay, so So you may try maybe to find an explicit construction, or maybe also you can try to find a maybe non-bipartite case. Okay, so still it's open. Okay. Okay, so well, they proved this one by using the concept of interlacing family. So what is the interlacing family? To understand the notion of interlacing families, we should know two more definitions. One is this one. So degree n-1 polynomial, real-rooted polynomial. Okay. So this is it. Interlaces and degree n polynomial. So this means that if we have this inequality here, so alpha sub 1, alpha sub 1, alpha sub 2, alpha sub 2. Oops. And here. So for example, we can think about this and this one. So this can be gx and this can be fx, or and this can be fx and this can be gx. Okay? So another definition is a bunch of, you can think about a bunch of polynomials in here. Okay. So this have a common interlacing. Okay. And if there exists a single polynomial, maybe say z, okay, this interlacing h of s sub j in here. So you can think about like this one. So these things and these things and those things, okay, but this one is a common interlacing for those things. Okay. We need the definition of interlacing family for the whole class. So let me get definition of interlacing theorem here. Consider finite set. So S sub 1 through S sub n, these are finite sets. Okay, and then you can think of for every assignment in the Cartesian product and here we define the polynomial, this one. Okay, so this is degree n, real-rooted. Real-rooted means all roots are real and coefficients are also all real. Real-rooted polynomial. With a positive leading coefficient. Okay. And then from from those polynomials, we define another polynomial. So for all k is equal to 0 through n-1, and every partial assignment S sub 1 through S sub k here. Maybe you can think of it here. So this polynomial is defined the sum of all here. So S sub k plus 1 and this n, S sub n, and here. So be careful, those guys are fixed, okay? And those are moving in here, okay? And this is defined also for k is equal to 0, means we can also have for the empty set. So this is the sum of all polynomials in here. Okay, so okay, then so this polynomial, okay, those polynomials. So in here, here. So this from our interlacing family. Okay. If for all k is equal to 0 to the n minus 1 and all S sub k. And here this polynomials, so these are fixed and these are just moving. So when S is sub I is equal just to plus minus 1, then there are just the two polynomials in here. Okay? So this has a common interlacing. As far as this is the longest definition that I know. Anyway, so it.
So where are the degrees? So you're willing to find interlacing for, so you have an n-1 degree polynomial interlaces.
Yes. So those polynomials are all degree just n.
Right.
All degree n, and all possible polynomials in here is all degree also n.
Right.
Yeah, just actually the degree n comes from the actually the number of vertices. You can think about it. I will give an example to understand this definition. Okay. But before that,
they just have a common interlacing. You're not giving. Oh, sorry.
What?
So initially you're given many polynomials, right? F of S1, S2, S3.
Depending on those sets, actually. Yeah.
Right.
Yeah, the assignment comes from the Cartesian product of those things.
The definition, right?
Yes.
Right.
So this is a definition for interlacing family. Yes. So the bunch of polynomials form an interlacing family and satisfying these conditions. Yeah. I will give you an example. Maybe that's easier to understand. Okay. Before giving an example, okay, let me give you a result related to this one. Okay.
What do you mean by like f of the last line? You have S1 of the SK and T is in SK plus 1.
Yes, this is given. So K is given. K is given.
Yeah.
K is given. So these are fixed one. And these are moving. So for example, S of K plus 1 is if there are two elements, then this is just a two element. There are two polynomials in here.
Oh, I see.
Yeah. We are going to have a time to understand this one. I mean, I will give you an example, okay? Okay. So, maybe I can write down in here. So, there is a theorem related to this one. So here. So here is the theorem. So Marcus, Billman, and Srivastava, they proved that. So those polynomials, okay, form an interlacing family. Then there exists an assignment. Thanks. In this Cartesian product, such that the corresponding polynomial, this one. Okay, so this is the largest root of this polynomial, and the corresponding this one is at most the largest root of the sum of all polynomials in here. Still, it's kind of it's hard to guess, okay, how we apply this one to a problem, right? Okay, so let me give you an example now. Yeah, can I erase this part? Actually, it is also true for at least. You can replace at least. Although they did not prove that part, but anyway, that is also true. So before giving an example, I will give you some more definitions. Okay, so yeah. Maybe this one is better. So here is a digraph. So let me write the purposes like this. Okay. The usual, adjacent, the matrix of digraph. Okay. So diagonal entries are all 0, and if there is a direction between 1 and 2 in this way, then you give a 1 in here. But there's no direction here, so we put 0. Like that, okay? No, so this is 0, and 2 and 3 this direction, we give a 1 in here, and 3 and 1, we give a 1 in here, like that. And then you can determine the characteristic polynomial of this one, so that's actually x cubed minus 1. So this means that we may have complex real roots in here, which are not real, okay? So, well, we know that the eigenvalues of adjacent matrix of just the graph, is well studied actually, okay, extensively studied. While the result of eigenvalues of a directed counterpart is, relatively sparse actually. Maybe one of the reasons is like this one. They may have no maybe real eigenvalues. So last year, Boyan and Boyan's student, Crystal Guo, and Li and Liu, independently, they created a new definition for the digraph like this. So they give a definition like this. So the 1 and 2 in this direction, we will give a complex number I. So I squared is equal to minus 1. But, well, in usual, adjacent matrix digraph, the other way is we give a 0. And in here, we give a minus I in here. Okay? Okay. And 1 and 3, this is directed in here, the other way. So in 2, we go I in here, and 3 this way, and this is minus I in here. Okay? And if you delete this one, then So you can determine the characteristic polynomial with this one, that's x cubed minus 3x, and you can recognize that the roots of these are real. Actually, this is called the Hermitian adjacent matrix of a digraph. The literally that's this Hermitian. Literally Hermitian, which means that all eigenvalues are all real. Okay. So to circumvent the situation, actually, they create this one to study digraphs, actually. So let me give a formal definition here. So an orientation of a graph G is a function sigma from the Cartesian product of vertex set. This is vertex set, and to the 3-element set 0 plus minus 1 here, such that the sigma uv is not equal to 0 if and only if uv is an edge in here. Okay. And this is the oriented graph corresponding this orientation. And
you don't care like if you have.
Actually, we care, right? So if uv and if there is in here, then we give just the I in here. Actually,
but in
yes.
this orientation, if you put 1 for that direction, then you don't want to put minus 1 too?
Well, yeah, we put minus 1 because see. Yeah, right.
Well, I think you need to add that too.
Right, maybe you, no, you don't have such a condition?
We have a condition, right? Yes.
So far this doesn't say that, right?
Yeah, I'm sorry. So, yeah. I will give you a definition for the Hermitian matrix. Sorry.
Okay.
Yeah. And this is the set of all orientation. Okay. And the Hermitian adjacent matrix of this one is the I times the sigma uv here. So if there is if it's an oriented like this, then we give you sigma uv actually is equal to I. Sigma uv is equal to 1. And here, and the sigma vu is the other way, so that's minus 1 here, like that. Okay.
Also, you need to have a condition that sigma uv is equal to minus sigma vu for every pair?
Right, for every pair, right, actually. Yeah.
In the definition of orientation?
Yes, actually, yes, right. So that's why I mentioned this one, yeah. Okay. And probably we want to label the edge sets like this, so maybe uj and vj. So u1, v1, u2, v2, um, vm. So we probably can have the end vertex like this, each one and this one, to have direction actually here. Okay. And if there is an orientation, then there is also, maybe you can put Sj is equal to sigma uj and vj, like that. So Sj possibly just 1 or minus 1 in here. Okay. And so this one is corresponding the polynomial. This one. Actually, this one is this one. So there is a one-to-one correspondence between the set of all orientation and the characteristic polynomial coming from the orientation actually here. Okay.
So you're making that definition now. Your polynomial f sub s1 to f.
Yes. Now I want to use this one. Yeah. To give an example in here. Yeah.
What is it? Like E of G is equal to that? Is that
E? What?
No.
E of G is the set of edges.
Yeah.
So I will label like this. So the number of edges is M. So
Is
for
the graph bipartite or?
no, it's not bipartite. So for example, yeah, they may be overlapped. So for example, this is U sub 1 and V sub 1, and I can say U sub 2 and V sub 2. Because those are the same. Yeah.
With the direction.
Yeah. Yes. Like this. Maybe something like that. Yeah. Okay. Then let's start with this one. So. And also V sub 2 and V sub 2. So let's think about the path with the two edges. Okay. So there are two edges in here. We have two options on each edge. Okay. This direction or this direction. Right? So what we can say, that's just 1 or minus 1 like that because of this one. Okay. So how many polynomials can we have then here? So if this is 1 and this is also 1, then we can have a f11 in here. Right? We can, maybe this one is easier to understand. So we can give a direction like this. Then we can have this polynomial, right? So this is same thing like this. We can give a 1, 1. Okay? So this is 1, 1. But we can give a minus 1 in here, right? Then we can have a 1 minus 1 in here. Okay? And maybe this can be minus 1. So minus 1, 1, and minus 1, and minus 1. So if there are two edges, then we can have 4 polynomials. Okay? So M, actually, you can think about this M is the number of edges in here. And S sub J is equal to just plus minus 1 in here. And now you can think about this one is the characteristic polynomial. But we know that the Hermitian matrix is literally Hermitian, which means that all eigenvalues are real. That means this characteristic polynomial is degree n, real-rooted polynomial with the positive leading coefficient. Okay? Because we switch it in here. So this is x to the... Actually, leading coefficient is just 1 in here. Okay, so satisfying that one, right? Now, if we want to show that those 4 polynomials form an interlacing family, then what do we have to do? Then we have to show this one, right? So k is equal to 0, 1. Because there are only 2 edges, right? So we should think about 0 and 1. So you want to show that f11 and f1 minus 1. So this is a common interlacing, right? So like that. And also, because you should check all k's and all assignment, right? So also f minus 1, 1 and f minus 1 minus 1 also common interlacing. And also you should check k is equal to 0. These are just k is equal to 1 case. So k is equal to 0, then f1 and f minus 1. So these polynomials also have a common interlacing. And f1 actually is equal to, by the definition, f1 is equal to f11 plus f1 minus 1. Okay, f minus 1 you can also see that. Okay. So this makes sense now.
Also, you don't care about the permutation of this size?
No.
You only care about the first k.
Right.
Oh, I see.
That's why they just show the existence. They do not care about the construction stuff in here. So to show that those 4 polynomials form an interlacing family, then we show that those 2 polynomials have a common interlacing, those 2 polynomials common interlacing, those 2 polynomials common interlacing. But there is a very nice theorem related to common interlacing. So this one. So Actually, many people proved this one, including Chudanovsky and Seymour in 2007. But the first one is actually 1980. But anyway, so those polynomials, the degree. Polynomials of the same degree with a positive leading coefficient. Positive leading coefficient. And so those polynomials have a common interlacing. The if and only if. Maybe we don't need the general version. So let's think about just the two polynomials. Sorry. It doesn't matter, but yeah. Okay. So this is the real rooted for all real, and let's say satisfying the sum. This is equal. So this is the convex combination. So for k is equal to 2.
Do you want lambda to be non-negative?
Oh, lambda, yes, non-negative. Say, thanks, non-negative. So actually, for k is equal to 2, we only needed that one because S sub j is equal to, each finite set just has 2 elements, plus and minus 1, okay. But anyway, so f sub 1 and f sub 2. So this has a common interlacing. We just want to show that lambda f1 plus 1 minus lambda f2 is a real rooted. Okay. For all lambda in here.
And real rooted means that every root is real.
Right. Every root is a real. And also the coefficients are also real. Okay. So can I erase this part? Okay, so what do we prove actually? Okay, so before giving our result, I need to give more definitions. Sorry, there are a lot of definitions. So this is the matching polynomial. Matching polynomial over graph G, the return. So let me use it this way. Many people actually use it this way, but anyway. Some people use for matching this one, right, mu, but I prefer this one, so let me use this one. Okay.
G prime?
Alpha prime, I'm sorry. Alpha prime, so that's why matching polynomial. Alpha prime. Okay. So this is the sum actually. So minus 1 to z, m sub z, x to the m minus 2 j here. So j. And here. And m sub j, this is the size, the number of matchings. With the size j. So for convenience, j is equal to 0, that's just 1. So m sub 0 is equal to 1, and m sub 1 is equal to the number of edges. Okay. And this is introduced to Hellman and Leib. It's a long time ago, so 1970, I guess 1973, but 1972 or 1973. Anyway, yeah. So they proved that for any graph, the matching polynomial is real rooted. Okay. Well, and you can also easily prove this one, you know. If alpha is a root of this matching polynomial, then when you plug minus alpha, still you will have 0. You can easily prove that, depending on n, but anyway. So if alpha is a root of this one, then you can also show that minus alpha is also root of this one. Okay, you can check. Okay, so what? Why did I introduce the one? Actually, we proved this one. For any graph, the expectation of all orientation, and here the characteristic polynomial of this one is equal to this one. Now, see why this matches in here? So this means that actually 1/2 to the m is the number of edges, okay? And this is the sum of all orientation in here. This one. Of course, okay, the sum of all polynomials, this one, is not exactly the matching polynomial because you need to multiply 1/2 to the m. But you know, when you multiply constant, you know, the root doesn't change, right? So, okay, what does this mean? If we show that those polynomials form an interlacing family, then there exists some assignment, which means that there exists some orientation. Okay, there exists some orientation satisfying this one. Okay, so this means that, so you can think about minimum because they exist. So minimum all orientation here. So this is the largest eigenvalue. Okay, say lambda max. This one, okay. So this one is m most. Say this is the largest root, absolutely largest root. I told you if alpha is a root of this matching polynomial, then minus alpha is also okay. So this is the largest, absolutely largest root of a matching polynomial. Okay. Okay, so this is m most in this one because of this. Okay, why did we care about this theorem actually? Well, actually, if a digraph has a small spectral radius, this is not spectral radius actually, but I told you the Hermitian adjacency matrix in this one. This Hermitian adjacency matrix is actually the eigenvalue of this Hermitian adjacency matrix is symmetric about 0. Symmetric about 0. This means that the largest eigenvalue is actually spectral radius. Okay, so we can actually change this as spectral radius. Okay, and if a digraph has a small spectral radius, then it is closely related to quasi-randomness. Okay. So if a digraph is a small spectral radius, then there are many orientation, okay, isomorphic to that kind of a digraph actually. Okay. So that's why we try this one, but it's not enough. Probably I want to erase this part. Can I erase this part? There is one more definition. Sorry.
We still didn't show that these are interlacing family. Right?
We didn't show that, right? But I'm not sure. But anyway, okay. So here is the definition for non-backtracking walk. So non-backtracking walk means so if this one maybe looks like this one. So this is non-backtracking means if we sub j minus 1 is not equal to we sub j plus 1. So non-backtracking walk of a graph satisfying this one. That means if there is in here, we go in, we do not back for every j. Okay. And then from here, we can define the universal curve of a graph. So
this is for the undirected graph, or
undirected graph, right? Universal curve of a graph G, we denote this like that. So written here. Okay. Maybe here. So you can pick a vertex, any vertex. Pick a vertex V, and from the vertex set of graph G, pick a vertex. And maybe you can pick 1, 2, 3, 4. Maybe you can pick one like that. Okay, one. Okay, and the vertex set of a universal curve is actually the set of non-backtracking walks starting from the vertex V. Okay, so here, 1, this is just also non-backtracking walk. And then you can go this way, 2. Okay, this is also non-backtracking, right? And 3 here. Okay, and okay, you can go 4 here. Okay. So the vertex, the vertices in the universal curve are adjacent. So this means that this is a continuation of this one, vice versa. Okay, vice versa. Okay, so look at this one. So 1, 4, this is a non-backtracking walk, but you cannot back in here. If you back, then that's not a non-backtracking. Okay, that's backtracking. So you cannot go further than here. But 2, you still cannot back to 1, right? But you can go 3. So go 3 in here, and 3 goes to this way, and 2 in here. So something like that. Okay. If a graph is just a tree, which means that if there is no cycle, then the universal curve and the original curve, they are same. But if there is a cycle, then you can have an infinite graph. Okay, and then you can think about the adjacent matrix of the universal curve. Okay, of course that's an infinite symmetric tree. Okay, and then you can think about, the spectral radius of the universal curve in here. Actually, they also proved this one. Marcus, Spillman, and Silva. So they proved that if it's not connected, then if there are 2 components, then if you choose a vertex in here and if you choose a vertex in here, then you cannot go to here. So we cannot have the same thing. But if it is connected, then choose it here and here. But anyway, you should go in here and here. So they are actually separate. So you can choose any vertex in here. So anyway, so for any connected graph G, okay, if alpha is the root of a matching polynomial, then the absolute value of this one is at most the spectral radius of a universal curve in here. What does this mean?
Minus infinite matrix.
Right, because the universal curve, each vertex has a finite degree.
Yeah.
Yes. So when you think about the sum, this one, this is, when we think about this is the sum, this is a convergent, okay? Then we define this one. And then, if the degree is finite, then it can be defined. Well defined, actually. So I want to skip this part. Probably I want to mention about that those polynomials form an interlacing family. Okay, so this is the last part. So Marcus Spielmann and Srivastava also proved this one. So there are a bunch of vectors actually here. Actually, they proved for the real vectors, but well, we just checked. This is also can be extended the complex vectors. Okay, and the P sub j is the real numbers, and here, and D is a positive semi-definite matrix. Okay. Then so this characteristic polynomial, this is a real root. it's
Any choice of A and B.
Yes. D is a positive semi-definite, and P sub j is real numbers between 0 and 1 here. So that is real. That proved this one. Okay, maybe I have no time to change this one. So probably, but I want to say this one. So by finding appropriate vectors and D, okay, then we can replace this guy. We can replace this guy is determinant xi minus hg sigma, and here, and you want to change S part is actually J, and this is sigma uj and bj is equal to 1 part. Okay, by replacing this one, then we can have this one also.
So what do you mean by adding? I mean, xi and d are matrices.
Xi? Where is xi?
Inside
Oh, this is x. Yeah, this is
inside the determinant. I and d are the matrices, but aj.
Yes, this is vector. C to the n.
Oh, these are
So, yeah, C to the n. Yeah. So you also need to find an upper vector in here. Then you can change like this. But I want to skip that part. Yeah. Okay, then.
Sorry, I'm still not clear. What are you summing over?
The S is equal to the J is in.
Oh, that's what S is equal to.
Yeah.
Oh, okay.
Yeah. Because we also need to define S, right? So J is related to the sigma is equal to 1 in here. Because we have only two options, 1 and
But doesn't this theorem say that for any subset of indices?
yes, but several indices in here. Yeah, breaking it.
Right.
Also, when you do it, is to come up with these vectors so that this polynomial,
Yeah.
this whole polynomial is equal to that one, the
Right.
expectation of.
Yeah. Then what happens? Then you can, well, we actually start with the example of the polynomial in here. So this one, then you can actually have an F11. Well, to show that F11 and F1 minus 1 have a common interlacing, so by this theorem, so you want to show that actually lambda F1, 1 plus 1 minus lambda F1 minus 1 is real rooted, right? By this theorem. So you can have this one actually from here. Actually. So how can we have this one? So P sub 1 is equal to lambda, and no, P sub 1 is equal to 1 and P sub 2 is equal to lambda in here. No, P sub 1 is equal to lambda, and P sub 2, well, 1 corresponding lambda in here, and 1 is corresponding in this one. So that was actually P sub 1 and P sub 2 and F11, and plus P sub 1. 1 minus P sub 2, F1 minus 1, because 1 corresponding in here. So because the S, in here, and the S is equal to this one, and plus P sub, 1 minus P sub 1 and P sub 2, F minus 1, and 1 minus P sub 1, and 1 minus P sub 2, and F minus 1 minus 1. So the sum of all things is also real rooted by this theorem. And then you need to find an appropriate values in here, okay? So to show this one is a common interlation, we want to show that this is a real rooted, then you want to choose P1 is equal to 1, and P2 is equal to lambda, right? So if you choose 1 and here, that's 1, and this is lambda, so lambda F11 and here, this 1 minus lambda in here, and if you plug 1, those are 0, right? So you show that this is a real rooted in here. So similarly, you can also show the other things, okay? Of course, we can prove generally, actually. So we can show that those polynomials form an interlacing by using this theorem here, and more generally. I'm sorry, that's the one. So this is all for today.